Welcome to the Deep Dive. Today, we're plunging into something that, well, it really feels like a turning point in robotics. For years, maybe decades, progress meant, stronger robots, better sensors, faster hardware, that kind of thing. But the conversation now, it's shifted completely. Our
Mhm.
sources today are all about Google DeepMind's massive Gemini Robotics initiative. And it signals this move away from robots just following a fixed script, the kind that only do one specific sequence of actions.
Towards general purpose intelligent agents.
That's absolutely the heart of it. The sources are really clear. The bottleneck isn't mechanical anymore. It's cognitive. It's shifted from the body to the brain, so to speak. So our mission here is to unpack the key technical leaps that let these machines reason better, adapt on the fly, and maybe most interestingly, from a strategic view, work across different types of hardware. Right, and the real hook, the thing that makes you think, okay, this is different, is that these robots can actually think internally now. They make little plans, they figure out what went wrong if they drop something. They can even, apparently, use the internet to solve physical problems they've never seen.
Yeah, it's the jump from a basic automaton to something genuinely helpful, genuinely capable. And to really get how they made that jump, we need to look at, I think, three main things. There's this dual model cognitive setup they have. Then there's this idea of agentic tool use, which sounds fancy, but is super interesting. And finally, the tech behind making one brain work in different robot bodies.
Okay, let's start with that dual brain idea because, splitting intelligence seems odd if you want general intelligence. Why two brains, not one super smart one? Is it maybe like a company structure? You have the CEO doing strategy and then the factory floor manager doing the actual work.
That's a perfect analogy, actually. Google DeepMind calls it a bifurcated cognitive architecture. And they did it because, well, trying to plan a complex, maybe hour-long task while also figuring out the exact microsecond force needed for each joint. It's just too much for one system. Computationally, it's a nightmare. So yeah, they needed dedicated systems for different kinds of thinking.
Okay, so who's the CEO in this picture? Which model does the big picture thinking?
That would be Gemini Robotics-ER 1.5. The ER stands for Embodied Reasoning. This is the CEO, the orchestrator. It's a specialized vision language model, a VLM. Its whole job is the high-level strategic stuff.
All right, so if I give it a fuzzy command, like sort the laundry, that's not very specific. How does this ER model handle that? What's the planning look like?
That's precisely its function. It takes that vague natural language goal, sort the laundry, and breaks it down into a logical sequence of simpler, concrete subtasks. Things like find an item, pick it up gently, look at the color, move it to the white pile, let go. This kind of high-level reasoning about space and time is key. And the sources mentioned they really put it through its paces, tested on like 15 academic benchmarks, RoboSpatial VQA, and others to make sure it genuinely understands the physical world.
And those simpler instructions, pick it up, move it there, they get passed down the chain to the foreman, the second brain.
Exactly. That's Gemini Robotics 1.5, the VLA, Vision Language Action Model. This is the action model, the low-level controller. It gets those single-step commands from the ER model and turns them into the actual physical movements, the specific joint angles, the speed, the force. It handles the how.
But things go wrong, right? Robots drop stuff. They miss. That can mess up the whole plan. How does this setup deal with errors? Does it just stop?
No, and that's crucial. They have what they call the agentic loop. It assures recovery. So the ER model plans a step. The VLA model tries to do it. Then the ER model watches what happened. It does success detection. If the robot, say, drops the sock, which happens all the time in the real world, the ER model sees the failure. It doesn't freeze. It adapts the plan. Maybe it tells the VLA, okay, try picking it up again, but maybe grip it differently this time. This ability to recover in real time is what makes it possible to complete longer, more complex tasks.
That real-time adaptation is impressive. But you mentioned something even more intriguing, embodied thinking within that VLA action model. It's not just reacting to commands, it's thinking first.
Exactly. The VLA isn't just a reflex. Before it actually sends the command to move the motors, it generates an internal monologue. Thinking trace, they call it. It's like a little microplan expressed in natural language. For instance, it might think, okay, need to put this block on the shelf. Plan. Find a clear path. Grasp the block firmly. Avoid that cup on the left. Lift smoothly. Release when I feel contact.
Hold on. The robot writes itself little notes before it moves. Seems like extra work. Why bother? What's the payoff for that?
Two huge benefits. First, performance. Actually formulating that microplan first makes it much more likely to succeed, especially on tasks that are, semantically tricky. It sort of pre-checks the logic. Second, and this is really important, transparency. Because it outputs that thinking trace, we humans can see why it did what it did. If it fails, you don't just see the failure, you see the flawed reasoning that led to it. That's massive for trust, for understanding, and just practically for debugging the system.
Yeah, I can see how that internal monologue would be gold for debugging. But what if the robot realizes it doesn't even have the info it needs to start planning? That's where things get really blurry between digital AI and physical robots, right? This agentic tool use.
Yeah. This is where you see a real leap towards general intelligence, I think. When the ER model, the orchestrator, hits a wall, when it needs some external fact, some piece of information not directly observable in the physical scene, it doesn't just wait. It can autonomously decide to use external digital tools, primarily Google search, to fill in that knowledge gap itself.
And the examples they give are pretty wild, like packing a suitcase for London. The robot does the normal packing stuff, but then the ER model thinks, London, checks the weather forecast online, sees rain is likely, and then decides on its own to pack an umbrella, something the user didn't even ask for.
It's proactive. It's goal-oriented problem-solving using outside knowledge. Another great example they mentioned is waste sorting. Imagine telling it, sort this trash. To do it right, it needs local rules. So the robot actually used web search to look up the specific composting, recycling, and landfill rules for San Francisco before it started sorting the items on the table.
Wow. Checking local ordinances and weather? That's applying knowledge in a way we haven't really seen before in physical robots. But intelligence isn't much use if it's stuck on one specific machine.
Which brings us to maybe the most strategically disruptive part, this cross-embodiment generalization, making the brain universal.
Right. This is the shift from thinking about a specific tool to potentially a universal operating system for robots. Historically, robot software's policy was super tightly coupled to the hardware. If you wrote code for a Frank arm, it only worked on that Frank arm. Its specific joints, its limits, its dynamics. Trying to run that code on, say, an Aptronic Apollo humanoid, forget it. Months of retraining, fine-tuning, massive effort.
There's a million-dollar question. How did they crack that? How do you make software work on bodies it wasn't designed for? The key is something they call the motion transfer, MT mechanism. The insight was to train a single VLA model, the action model, on a huge data set drawn from wildly different robots. We're talking data from little desktop arms like a Lola, industrial arms, big humanoids, the works. By learning from this incredibly diverse fleet, the model starts to understand the abstract concepts of motion, physics, and achieving goals, independent of the specific robot body.
So if I use that OS analogy again, it's like writing an app that understands the idea of displaying text or playing audio so well that it can run on an iPhone, an Android phone, a Windows PC, even though the underlying hardware is totally different.
That's a great way to put it. And the strategic implication is huge. It means one VLM model can control lots of different robot types without needing specific fine-tuning for each one. Think about the network effects. A skill learned improving a task on one robot type. Maybe a Franca gets better at handling delicate objects. That improvement instantly benefits the entire fleet of different robots running the same VLA model. This really shifts the value away from the unique hardware itself and puts it squarely onto that shared universal AI brain.
Okay, let's ground this a bit. What does this universal brain mean for actual physical skill? How precise can it be if it's so general?
Well, the demos are pretty stunning, actually. The sources show the VLA model doing things that require real dexterity, like folding a small origami fox, carefully using tongs to pick out specific ingredients for a salad, or zipping up a Ziploc bag. These aren't clumsy movements. They require fine motor control.
And the generality really comes through too, right? Like the example of slam dunking a toy basketball. It wasn't trained specifically for slam dunking that toy. It had to understand the semantics, what slam dunk means in context, and apply its general knowledge of motion to make it happen. And it worked on the first try.
Yeah, and given these capabilities, especially the cross-embodiment part, it makes total sense that Google DeepMind is betting heavily on a platform strategy.
Yeah.
They're signaling pretty clearly the AI brain is the core asset, the most valuable, the most defensible part of the whole robotics stack.
And they're already building that platform ecosystem, aren't they? You look at their trusted tester program, and get some heavy hitters, Aptronic with their Apollo humanoid, you've got Boston Dynamics, Agility Robotics with Digit, Universal Robots doing industrial stuff. It really looks like Google is positioning Gemini Robotics to be the standard OS for intelligent machines.
But with that power comes responsibility and control. They're managing access carefully. The reasoning part, the ER 1.5 model, that's becoming more widely available through their Gemini API for developers to experiment with. But the action model, the VLA 1.5, the part that actually moves the robot that's restricted to select partners, which makes sense, right? That's the part with direct physical agency, so safety is paramount.
Which pivots us neatly into the competitive landscape. Because understanding how the big players are tackling this is key. It seems like there are fundamentally different bets being placed.
Absolutely. If you break it down, Google's Gemini Robotics is very much AI-first, platform-centric. The core belief seems to be software intelligence is the key differentiator. Decouple the brain from the body, build a platform, leverage network effects from diverse hardware partners.
Okay, then you look at Tesla and Optimus, totally different approach, right? It feels much more vertically integrated and maybe data-centric.
Exactly. It mirrors their self-driving strategy, rely heavily on vision-only neural networks. The bet seems to be that the entity with the most and the highest quality real-world data leveraging their car fleet using human video demonstrations will ultimately train the most capable AI. It's a data quantity and quality play.
And the third big player, Boston Dynamics with Atlas, they come from a different world altogether.
Right. Their legacy is hardware-first, dynamic-centric. They arguably already have the most physically capable humanoid platform out there. You see it doing parkour, incredible feats of balance. Their bet seems to be that a superior physical body, one that deeply understands physics and dynamic interaction, is the essential foundation. And now they're layering advanced AI, like large behavior models, on top of that superior hardware base. So yeah, three really distinct philosophies, all aiming for capable humanoid robots.
Fascinating. But whenever you talk about putting powerful general AI into machines that move around in our world, safety has to be front and center. I mean, a mistake in software online is one thing. A mistake by a physical robot, that's different.
Oh, absolutely critical. DeepMind sources talk about using a multi-layered safety approach. They call it the Swiss cheese model. The idea is that no single safety layer is perfect. It has holes, like Swiss cheese. But if you stack multiple layers, the holes are unlikely to line up. So you have the traditional stuff, collision avoidance sensors, limits on force, that's physical safety. But critically, you also need semantic safety.
Semantic safety. Okay, so that's about the robot understanding the meaning and context, refusing to do unsafe things like don't hand scissors to a toddler, even if told to. That seems hard to measure. How do you quantify if a robot is semantically safe?
They developed a specific tool for this, the ASIMOV benchmark,
Yes.
named after Isaac Asimov. It's a public benchmark designed explicitly to test the semantic safety. It throws generated scenarios at the robot brain, scenarios often based on real-world human injury data, to see if it makes safe and ethically sound decisions. It's about creating a standardized, open way to evaluate that crucial aspect of behavior before these things are widely deployed.
That public accountability is good. Now, shifting back to control for developers for a second, there's this really neat feature mentioned, the thinking budget. It sounds like I can literally tell the robot how much time to spend thinking. So when would I want to crank that budget way down, make it react fast?
Yeah, the thinking budget lets developers tune that trade-off between speed and depth for the ER reasoning model. A small budget means low latency, fast response. You'd use that for simple time-critical things, maybe quickly identifying a large, obvious object, or a reactive movement like getting out of the way of something.
And a large budget for the complex stuff.
Exactly. More budget means more inference time allocated for deeper reasoning, complex planning. You'd use a larger budget when the task needs careful interpretation, like counting lots of small items in a messy scene, or figuring out that whole proactive packing list we talked about earlier, considering the weather and destination. It lets you optimize performance. Do you need speed right now, or do you need more intelligence?
So pulling it all together, DeepMind isn't just framing this as building better robots, they're connecting it to the grand challenge of AGI, artificial general intelligence.
That's the underlying research driver, yes.
Yeah.
There's a strong hypothesis, not just at DeepMind, but in the broader field, that true AGI might actually require physical embodiment. The idea is that AI trained purely on text and images, digital data, fundamentally lacks a deep, grounded understanding of cause and effect, of basic physics, of common sense. By forcing AI to interact with the messy, unpredictable, physics-bound real world, it gets constant, unambiguous feedback. Things work or they fail. That grounding is potentially the richest learning environment for developing truly general intelligence. Robotics might be the crucible for AGI.
It really feels like a significant leap we've covered today. Moving beyond just automation, towards robots that can reason, adapt, learn, even tap into the world's knowledge online to operate physically. The focus has undeniably shifted to the AI, to the brain, not just the metal body.
And that shift, especially combined with that cross-embodiment capability, the universal brain idea, it really sets up some profound questions for us to think about. So here's something to mull over. If the future really is about the AI brain, and Google's building this universal platform while others focus more on integrated bodies, what happens ethically and maybe regulatorily when a single AI model learns a complex, potentially sensitive skill on one robot, let's say, handling hazardous chemicals safely, and that knowledge can be instantly deployed, perfectly replicated across thousands of physical different robots worldwide? Who's liable if something goes wrong? How do you control that spread of capability? What does universal knowledge truly cost when it's embodied? That's something we'll definitely need to grapple with.